Friends, we've been learning about logarithms and exponents, the relationship between the two, and then properties. And now we're going to use those in order to solve um, equations and inequalities that have logarithms and exponents in them. So a quick review, properties of exponents that you should be familiar with, how those exponents are combined when you're multiplying bases, when you've got the base to the power to another power, etc., negative exponents, and then the logarithmic properties as well, product, quotient, power property, etc., and then converting between the forms, exponential and logarithmic forms. It's important to be able to go back and forth between the two. Okay, so when you've got an equation that only has one one logarithm or one exponent in it, here are the steps for doing that. First of all, isolate the exponential or the logarithm, logarithmic expression on one side of the equation. Then you're going to write the equation in the alternate form. Switch between exponent and log. You'll see what it looks like when we do the example. And then solve for the variable, simplify, round, etc., as you're asked to do. So let's take a look at an example here. Okay, so here we have 4 to the x minus 2 equals 7. Okay, well, first of all, I need to isolate the exponent, the exponential expression, and I'm going to do that by adding 2 to both sides. It's very simple. So 4 to the x equals 9. Now I'm going to rewrite this. Okay, so this is log base 4 of 9 equals x. And so that's it. We can leave it that way. You can put this into the calculator if you want. You can put in log 9 over log 4, and that would give you the solution, or if you can change the base, or just leave it this way. This is an acceptable answer. If you were to find whatever the decimal turns out to be that this calculates to, that is the same value as this. It means the same thing as this expression. So we can leave it. Now, let's try this one. So this is, again, I need to get the exponential expression by itself. So this is 2 to the x plus 3 equals 31. Sorry, 21. Let's learn my arithmetic, 21. And so this is going to be log base 2 of 21 equals x plus 3. I still don't have x by itself. So x equals log base 2 of 21 minus 3. And that's it. That's the answer. Can leave it that way. Okay, so I'm trying to get e to the x by itself, and that includes getting rid of that 4. So minus 3, so this is negative 10 over negative 4 over negative 4. So this is 5 over 2 equals e to the x. So this is going to become natural log. So remember, log base e is natural log of 5 over 2 equals x. Okay, and again, we leave it that way. That's going from exponent, right, solving exponentials. Now let's see what it looks like solving logarithmic equations and expressions. Okay, so let's see. I'm going to get the logarithmic expression by itself and then make it exponential, write it in a different form, and continue to solve if I need to. So first of all, this is going to be 2 log base 3 of x plus 3 equals, subtracting 4 from both sides, so equals 6. Divide by 2, so log base 3 of x plus 3 equals 3. So this is 3 to the third power equals x plus 3. So I'm going to subtract 3 from both sides. So 3 to the third power is 27. Right, so this is going to be 27, but 27 minus 3 is 24. Next one, same idea here, right? So log base 5 of 2x minus 1 equals, subtracting 2 from both sides, so 2. So now I have 5 squared equals 2x minus 1. So this is 25. I'll add 1 to both sides, so 26 equals 2x, and so 13 equals x. Next one. All right, so multiply 5 to both sides, natural log of 2 minus x equals 5. So now e to the 5th power equals 2 minus x. Okay, so this is going to turn out to be, so I can subtract 2 from both sides, but then I multiply everything by -1. So x equals 2 minus e to the 5th. And I can leave it that way. Don't have to simplify any more than that. Okay, now that's if I only have one exponential or one logarithmic expression. If I have two, then there are a couple of options here. So looking at our different forms, right? If we have form one, looking at what we've got written here, right? If it's this kind of a form, right, then that's doing what we've already done. But if there are two logarithms, right, we end up with this kind of thing. As long as they have the same base, what we can then do is say that x equals y and solve it that way. Uh, However, a couple quick things. Check for what are called extraneous solutions. So when you do this solving x equals y and you find whatever the variable is that you're looking for, you have to make sure you're not going outside of your domain. There are domain restrictions when you've got logarithms, so you've got to pay attention to that, and then exclude those from your solutions. Another important note: a log of x plus log of y equals log of z. That does not mean that x plus y equals z. Uh, it might, right? Some possible circumstance, but that's not what it means, right? Log of x plus log of y equals z. That's a different thing. You got to pay attention to the logarithmic properties when you're solving these equations. So let's take a look, and we're going to get an example of that right away in example 3a. So right away we begin. Now log, it's just written log. There's no base, so we assume it's base 10. That's the standard convention, and we can combine these, right? But they're multiplied, so log base 10 of 3 times x plus 4, that's all in parentheses, equals 5x, sorry, log 5x minus 2. I'm getting ahead of myself. Okay, one quick thing too, before we go any further. From log of x plus 4, I know that x has to be greater than -4. And from this one, I know that x has to be greater than 2/5. All right, but then 2/5 is greater than -4. So this is my domain restriction that I'm dealing with for my solutions. Okay, now I have log, same base, and these two expressions. So that means that 3x plus 12, that's 3 times x plus 4, right? So 3x plus 12 equals 5x minus 2. And now I just have to solve for x, and it turns out that x equals 7. Some simple algebra, and that is greater than 2/5, so it all works out. Okay, so you're seeing how this works, of course. Again, so here I'm going to combine. These are subtracted, so natural log of x plus 1 over 3x minus 5 equals natural log of 7. And so now it's the same base, so I can just write x plus 1 over 3x minus 5 equals 7. Solving here, write x plus 1 equals 21, x minus 35, etc. And then we should end up with x equals 9/5 when you do the algebra. And checking our domain restrictions, x has to be bigger than -1. Here, x has to be bigger than 5/3, but 5/3 is bigger than -1, so that's our domain restriction. 9/5 um, is that bigger than 5/3? It is. So it works. Right? Got to check it. Right, 9/5 is like 1.8. 5/3 is 1.67. So we're good. We're where we need to be. Okay. Again, all these have the same base. Domain restrictions, x has to be bigger than -2. x has to be bigger than 3. That's it. So our domain restriction here is that x has to be greater than 3. Same base, so we can combine log base 3 of x plus 2 times x minus 3. Okay, it's going to get a little messy. And then log base 3 of 14. Okay, so this is going to be x plus 2 times x minus 3. We're just going to FOIL this and then bring the 14 over. So this is going to be x squared plus 5x, or sorry, minus x, minus 6 equals 14, subtract 14. So x squared minus x minus 20 equals 0. So we end up with x minus 5 times x plus 4 equals 0. Our solutions are x equals -4 and 5. However, x has to be greater than 3. And so -4 is out. So x just equals 5. And now, again, same kind of idea. So this is natural log of x over 3 equals 2. Now, I only have, when I've reduced it, now I only have one logarithmic expression, right? So now I can do the switching between exponential and logarithmic, or logarithmic to exponential form, I should say. So e squared equals x over 3. So x equals 3e squared, like that. This is fun, isn't it? I actually think it's really cool how all this stuff works. You can go back and forth, and the possibilities that it opens up. Like I mentioned before, we use this in my AP Physics C class, some of these properties, and the students were like, oh yeah, they remember these things. But I think it is really beautiful how it all fits together, and you can get from one idea to the next. And if you can understand the proofs, kind of the arguments behind it, the way that exponents work, and therefore the way that the logarithms work, it increases your understanding, but also hopefully lets you see the beauty in it a little more as well. Let's continue with some more of these examples. Okay. So here are domain restrictions. X has to be bigger than 0 for that. And here, X has to be bigger than -7. So X is greater than 0. That's our big domain restriction for this one. Uh, so the way we're going to simplify this, I want to keep the same base, but I've got this 3 in front. How do I kind of get rid of that, you could say? Well, the 3 in front can become an exponent of the 2. So this is log base 4 of 2 to the 3rd power, which is 8. But I'll leave it as 2 to the 3rd for now to make it clear where that went. And now, continue simplifying things. So log base 4 of, right, x, and then the subtraction turns into division. So x over 2 to the 3rd is log base 4 of x plus 7. Same base. So I can take those expressions, set them equal to each other. So x over 8 equals x plus 7. So x equals 8x plus 7. And so x is going to end up being, oh yeah, whoops. Check my arithmetic here. 8 times 7 is 56. So I'm going to have negative 7x equals 56. So x equals negative 56 over 7. Now, the problem is this solution is less than 0. What does that mean then? That means no solution. Sometimes that happens. But again, you've got to see it. In order to see it, you've got to check that you've got the domain restrictions and that you're following them when you have your solution at the end. Next, so log of x minus 2 equals log of x minus 7. So I think there's a typo here. I think this should say instead log of x minus, this should say 3 log 2 equals log x minus 7. Okay, domain restrictions. X has to be bigger than 0. Also, x has to be bigger than 7. So 7 is bigger than 0, so x greater than 7 is our domain restriction. So I'm going to combine these again. So I'm going to do the same thing I had done before with the 3 and the 2. This is log x minus log of 8, right? 2 cubed is 8 equals log x minus 7. So very similar to what we did before, but let's see how it's different. So log of x over 8 equals log of x minus 7. So now I can um, set the expressions equal to each other. X over 8 equals x minus 7. So x equals 8x minus 56. And so now negative 7x equals negative 56. And the solution is x equals 56 over 7. So 56 over 7 is 8. And that works. This is actually a little bit different from what it has in the answer key. Um, yeah, actually, it's a totally different problem from what was in the answer key. And so what I've done here is actually a problem that's different from what's in the entry key, and it's also different from what is here. But anyway, there it is. So here's another example. Let f of x equals natural log of x plus 15 minus natural log of x, and then we have an expression for g of x, natural log of x plus 3. We want to find the values where the graphs intersect. So how do we find the values where the graphs intersect? The way we do that is we set them equal to each other, and then we solve. So let's set them equal to each other. Natural log of x plus 15 minus natural log of x. I'm going to set that equal to g, which is natural log of x plus 3. So that's the log of x plus 15 over x equals natural log of x plus 3. And now I set the expressions equal to each other because it's the same base. So x plus 15 over x equals x plus 3. So x plus 15 equals x squared plus 3x. So this is going to be 0 equals x squared plus 2x minus 15. Now that's a little bit different from what I have over here. Why would that be? Oh, because what's in the answer key again is different from what is here. They have natural log of x plus 10. But anyway, we can continue with this. 0 equals x minus 3 and x plus 5. That works, right? So x equals negative 5 or 3. Now we need to check our restriction domains. Um, Here, x has to be greater than 15. X has to be greater than 0. Sorry, x has to be greater than negative 15. And here, x has to be greater than negative 3. So really our restriction is that x has to be greater than 0. And so x equals 3. It's the only one that works that excludes negative 5. Check my arithmetic that I did that right. I think that works. That factors to x minus 3 and x plus 5. Figuring out and talking as I go. So let's try example 6. Let's see if this is the same here. The answer key. Well, it looks like this one's the same. Good. So now we've got an expression for h of x and k of x, and it says what are all the x coordinates of the points of intersection of the graphs h and k? Again, we set these equal to each other to find where that would be. So log base 3 of 2x minus 3 plus log base 3 of x plus 4 equals log base 3 of 8x plus 2. Okay, So these are being multiplied. Log base 3 of, wait, let's see what's going on here. Oh yeah, we're good. So this is 2x minus 3 times x plus 4. Again, all of this being multiplied equals log base 3 of 8x plus 2. So we're going to multiply this out, right? Again, same base. So now we eliminate the logs. They're not canceling out. That's not what's happening, right? We know those two expressions are equal, so we set them equal to each other. And so this turns out to be 2x squared plus 5x minus 12 equals 8x plus 2. Okay, and then this simplifies to 2x squared minus 3x minus 14 equals 0. And this actually factors to 2x minus 7 and x plus 2. So our possibilities are x equals 7 over 2 or x equals negative 2. Our restriction domains, let's take a look at that to make sure we don't have any illegal solutions. Here, x has to be greater than 3 halves. Here, x has to be greater than negative 4. Doesn't matter because the 3 halves. And here, x has to be greater than negative 2 over 8 or 1/4. So this is our restriction domain. Let's look at our solutions. So x equals negative 2 is ruled out, and we have x equals 7 over 2. That's our solution. So that's the x value of the place where these two functions cross in the xy axis. Okay, now, so we've seen multiple logarithmic functions. Now let's look at this with multiple exponential functions. Works the same kind of idea. Works the same kind of way. So here they have the same base, and so those exponents then must be equal to each other. So 5x minus 1 equals 2x plus 7. Simplify this, and 3x equals 8. So x equals 8 over 3. Very simple. Nice and easy. Here, we don't have the same base, right, with example B. And so we have to create the same base. How are we going to do that? Well, 8 is the same thing as 2 to the third power, right? So that's like 2 to the 3 times 3x minus 2. That equals 2 to the x plus 5. And so 9x minus 6, that's the 3 times 3x minus 2, equals x plus 5. And we solve this, x ends up being 11 over 8. Skipping over some of the algebra, which I'm sure you know how to do. Very simple. If you're watching this video and you don't know how to do the basic algebra, you need to go back a couple of years. C. Same kind of thing here, right? Except that 9 and 27, I don't have a way of getting a common base of 9 from 27. However, I can get the common base of 3 from both of these, right? So this is 3 squared times 2x equals 27. This would be 3 cubed times x plus 2. So 4x equals 3x plus 6. So x equals 6. And the last one, 1 half. So the 5x plus 7 equals 4x. Again, got to get creative and finding the common base. The common base is going to be 2, except this is going to be 2 to the negative 1 times 5x plus 7. And this is going to be 2 to the 2x. So negative 5x minus 7 equals 2x. So let's see, this is going to be negative 7 equals 7x. So we end up with x equals negative 1. And so that's it. A lot of examples of solving logarithmic equations and exponential equations. How do you do that? Using the properties and going back and forth between the forms of the exponential and the logarithmic. So thanks for watching. Don't forget to like and subscribe.